Hello everyone, it's Monday, and we are solving Sunday's Advent of Go problem today, because I didn't do anything yesterday. Um, so, a couple of things to catch up on. Day 19 was um, pretty easy, part 1, and I, I solved it by doing a regular expression generator, generating the regular expressions and then running everything through that. That worked. And then part 2 went and said, oh, well, we're going to give you now some rules. We're going to modify the rules slightly. And the rules are going to be such that they don't actually work with regular expression. And in particular, the thing that we were challenged with was the fact that there was a recursive regular expression rule which said essentially prefix. The rule was either prefix suffix or prefix rule suffix. And what that means is that essentially you have, the requirement was that there be as many prefixes as there were suffixes. And that's not something that a standard regular expression grammar can do, because that requires essentially counting or a recursive definition. Now, there are regular expression packages you can get as plugins for certain languages that will do that. Go's definitely does not. Python's native one does not, but you can get one that does. And so we had to tackle the problem a different way. So I decided to tackle it by saying, okay, well, let's count the number of prefixes and the number of suffixes. And if the number of prefixes is greater than the number of suffixes, then we the system will, then it's correct, because it's the greater than was essentially part of the requirement. There were two pieces. One was prefix, at least one prefix, followed by as many prefixes as suffixes. So that meant that the definition was greater number of prefixes than suffixes. And I then wrote a loop to do that, basically chop off pieces and check. And then I got the loop wrong. And so it took me a while staring at it to figure out what was going on there. Eventually managed to get it, and it's fine. And so that's up on GitHub if you want to look at it. And then today, okay, our problem today. Let's actually just get into where we are today. I took an advanced look at it and started writing some infrastructure, because it didn't seem like there was that much point to writing what should be fairly basic code on the stream. So let's show you what I'm talking about. So the puzzle we're dealing with is called the Jurassic Jigsaw. And what it is that we have a collection of these tiles, which each tile is a 10 by 10 array of bits. And collection of tiles, and one of the things is that they overlap slightly. The border on tiles, you can piece them together by matching the borders. Kind of like happens when you assemble a jigsaw puzzle. The thing about it is that these pieces are two-sided, square, and possibly rotated or flipped. So we have to match borders, but we have to match borders in a way, but basically doing what you do with a jigsaw puzzle. You kind of twist and turn and find the matching edges and pin them together. So what I did was I wrote the parser for this. I decided on my data structure, wrote the parser, and wrote some transformation tools. So I'm going to take you through those real quick to show you what I did. So the data format here is tile ID. Our solution consists of essentially reporting the IDs of the corners of the puzzle. And each tile then consists of dots and hashes. Excuse me. Each tile ID consists of dots and hashes indicating and whether the bit is colored in or not. So since these are basically 10 binary numbers, each of which is 10 bits, the easiest way to store these is as an array of integers. And so I wrote a parser that basically just pulls the, first thing it does is take the contents of a tile, pull out the first line by extracting the number from that line and converting it to an integer. That's the tile ID. And then I just convert dots and hashes to zeros and ones and parse it as an integer, as a binary integer, to get a number out of it. Now, my data structure for a tile is the ID of the tile, the data containing the tile, but I also have pulled out, we might end up changing this, but for right now, what I did was actually pull out 4 integers, top, bottom, left, and right, which are the edges, the values of the edges. Now, top and bottom are just the 0th element of the array and the 10th element of the array. The left and right edges, we have to be able to look at, we have to be able to extract a binary number from a vertical slice of a particular bit in all the arrays. So that operation is what I've called vert. And you pass it in which bit you care about, a mask corresponding to which bit we're dealing with. So the 0 bit, the mask is a 1. The 1 bit, the mask is 2. The 3 bit, the mask is 3. The mask is 4. Sorry, up to the last bit where the mask is 2 to the 10th or 1024. So, so I define some constants here. My tile size is 10. We have 10 by 10 tiles. That's not going to change, but it's nice to put it in and have that be parameterized. The low bit, of course, is 1, because it always is. The high bit is 1 shifted left by 9 bits. Oh, and by the way, I made a mistake here when I was messing with this. I didn't use the parens here, but the shift operator binds more tightly than minus. So what I ended up doing was 1 shift left by tile size and then subtracting 1 from it. So I got 1023 instead of 512. By the way, I got that wrong a minute ago. So the high bit is 512, not 1024. Anyway, had to add the parens and that worked. So vert allows me to take a vertical slice of things, and then when I look at this update edges function, I essentially say the top is the 0th item, the bottom is the last item, left is the vert of high bit, and right is the vert of low bit. So now I have all the edges values. So we have to be able to flip the tile vertically. And a vertical flip is merely reversing the elements in the data array. So vflip returns a new tile, which is a version of the tile flipped. So I just iterate through the array and assemble the new tile in reverse order. And the other thing I'm doing is I'm adding a string called transform, which shows for a given tile how many times it was transformed and in which ways, so that, if I vertically flip a tile, I append a V to that transform string. If I horizontally flip a tile, I append an H to it, and if I rotate the tile, I append L to indicate the tile was rotated to the left. Great. That covers that. So, okay. So a vertical flip is just reversing the elements in the data array. A horizontal flip means reversing the bits in each element in the array. So I go through the array in order, and for each of those I reverse its bits. So reverse bits is reverse 10, because I'm not reversing all the bits in the word, I'm just reversing 10 bits in the word. So the way I do that is that I take the value I'm trying to reverse and I build a new value, and I keep taking the lowest bit and shifting it in from left to right. So basically I take the lowest bit in, and I put it in the new word, and then I shift the new word left, and I shift the old word right, and it's kind of like you're doing this rotation of the bit from, the word from this one into that one, and it comes out in the reverse order. So that's what reverse 10 does. And then rotate left takes a tile and says, all right, we're going to take this top word and we are going to rotate it. We're going to make it, actually I did it the other way. We're going to take from the 0 bit to the high bit, we're going to do a vertical slice and then use that as the first word. And then we're going to take the second bit, rotate it, and use it as the second word. So it's vertical slice, rotate in, vertical slice, rotate in, vertical slice, rotate in. And that by doing that from the lowest bit to the highest bit and loading them in top to bottom order, that is essentially taking the entire tile and rotating it to the left. And I'm sorry, I don't turn my brain around when I'm looking at the camera, and so everything I'm doing is backwards for you. And sorry about that. So I have rotate, flip, horizontal, flip, vertical. So those basic operations are there. So I have the ability to read a tile. I have taken tile and given it a string, which is compatible with the stringer interface in Go, which basically tells the tile to print it, to render itself at the same way it came in. So with the one thing is that I append to the first row an indication of whether it has been flipped or rotated. And then, so then just to test that, and this is as far as I've gotten so far, I loaded the sample file and I just printed each tile. And what I got out is the same as what I get in. So if we look at the top of this file, we can see tile 2311 in my output, which was parsed and regenerated, is the same as tile 2311 here. Now, if we, so that gives us basic data structures. Now the question is, how are we going to solve this problem? So I think what I'm going to do, this is now where I'm solving the problem live. I think what I want to do is I want to take each tile and I want to generate the possible rotations and flips of that. And then store those in a map. Well, wait a minute. So I need all of the tiles with all of their edges, and I need the like all the permutations of all the tiles with all their edges, and I need to find matching top, bottom, left, right for those. Now this is interesting because one way to do it would be to generate rotations, pull, and then store all the top, bottom, left, rights. But another way to do this that's probably faster is to see if I look at a single tile and I get its top, bottom, left, right, and then I get the reverses of its top, bottom, left, right. Now I know all of the things in all of the tiles that could possibly match anywhere. And then I start going through looking for matches between tiles and assembling them together in a way that makes sense. So the question is whether there are going to be any duplicates of those or whether this is all unique. So one of the questions I don't know here is, if we find a match, is it a guaranteed match, or is it the case that actually, some of these pieces are going to fit together wrong, and we'll have to try again by moving them around. I guess one way to tell that would be to generate all of these. So top, bottom, left, right, plus the reversed version of top, bottom, left, right for all the tiles. Throw all those integers in a map and count them. We should get 8 per tile. Divide by 2, because if they're perfect, if there's exactly one match for everything, then it's simply a matter of having a there's going to be 2 of everything. So actually, if we do a map and we add 1 to the map every time we see value, we can look at the values in the map and see how many we have. So actually, let's try doing that first. So this is my little pun. Text tiles are the text versions of the tiles, and tiles is going to be I'm going to make slice a tile, and tiles equals append tiles tile. I don't need to print it right now. And edges is going to be map of int to int. Oh, we got to make that too. And so we're going to say so right now I have my tile structure has the edges as individual variables, top, down, left, right, because I figured I would be looking at them individually. But it might be easier if they were in a slice of edge values. With well-known positions. Okay. So here's an interesting thing. So when we assemble this structure, what we are looking for is tiles. Just like with jigsaw puzzles, the easiest things to assemble are the edges first. And so if we go through and after we build this map, we count the number of edges that are matched for that particular tile. A tile that has 2 adjacent edges mapped is a corner. A tile that has 2 edges mapped is a corner. A tile has 3 edges mapped is an edge. A tile has 4 edges mapped is a middle. And so what we'd like to do is to find the corners. And that actually gives us the simplest answer for the first part of the puzzle, which is because all we have to do is tell it which tile numbers are the corners. So that's really easy, and we can do that and figure out what the second half is. So let's do this. Let's go back, adjust our tile data structure, and then we can go back and finish what we're doing here. So the tile data structure, instead of having, we're going to have edges, which is slice of all right, here's where we're going to do this. We're going to make another set of constants, and we are going to have the top. Let's go clockwise, and we'll go top, right, bottom, left, and then we are going to do the flipped versions of all of those as top, right, bottom, left, and we'll create constants for all those. So top, and it's funny, I forgot about iota the other day when I was doing this for a previous solution. I actually put in explicit constants for all of these, and then I had to change them later. Iota is a lot easier. So with Go, when you're defining constants, if you use iota, it's a value that starts at 0, and every time you repeat it, it increments for each group. And if you leave off an assignment, if you leave off the equals on when defining a constant, then the right side of that element is repeated, and so if you use iota, then it just says equal iota all the way down. If you'd use something like 1 shift left iota, and you're going to create a selection of masks, it will repeat 1 shift left iota, but increment iota all the way down, and so you'll get 1 bit, 2 bit, 3 bit, 4 bit kind of thing as you go, which is also very cool. So we can just go top, right, bottom. Why is this? There we go, sorry. Left. That was not a time saver, but so, right paren. So now we have our indices for getting at the various elements of the edges. And So now we have the edges, and here we have a update edges function that I've been calling to update these values. I'm going to put it up next to tile to make it more obvious what's going on. And instead of saying this, we're going to say edges top oh, it's t.edges. And now we're going to do the inverted ones. And then all of these are going to be t.edges there. Okay. So now we have all the values in the edges. And we want to add all of those to our map. Oh, and actually the last thing we're going to do here is we're going to oh yeah, no, we don't have to modify the tile structure for this. Now, so we have oh, okay, so wait, edge map is not the map I was thinking of making. What I want is a map of the number of times. We need two maps. We also need a map. Now, actually, I guess I will just modify the tile data structure. Say, which edges of the unrotated tile match. So. And I've got a bad, oh, because I don't have a close brace, it's not even letting me save anything. There we go. Okay, now so what we want to know here is whenever we see a match in a tile between two edges, we're going to go to both of those tiles and we're going to say your top edge matches that one's bottom edge. And let's make a new tile function because now we've got something that needs to be initialized. So we're going to func new tile and it's just going to return an empty tile. Because we use that a lot. Or new empty pointer to a tile. Or pointer to an empty tile. That's a better way to put it. So return ampersand tile curly brace ID. Tiles always need an ID. So we can do the int ID transform and data and edges are both arrays, so we don't have to initialize them. They were initialized to what we want them to be, which is zeros. Matches needs to be make int question, should this be a map? If we map this is a cute trick, but I'm not going to use it because I'm about to create a type. Edge is an int. And then this becomes an edge. And what we're going to do is we're going to say which tile index is, oops, sorry, which tile indexes are we matching to? Why is makeup set? I'm just thinking for safety purposes or for documentation obviousness, if we go to type ID, also an int, then it becomes, oh, okay, is now map edge ID. There. And so when we construct a new tile object, now we can say rotate left, new tile, t.id, and now this is going to rotate left is going to return a new tile. H-flip is going to return a new tile, and it's going to be the same thing. Copy here, paste there, except that now the transform is H, and I can get rid of this line, and this one becomes that, but the transform is V. Get rid of that line, and this becomes star tile. Okay, so those are my transformation operations. Parse is still good, except that instead of doing this, I'm going to new tile. It's going to return a pointer tile, and this is now going to happen after we've figured out what the idea is going to be. ID, and it has, since it's a new tile being parsed, we have no rotations, so we leave that alone. And then we update that, so that's good. And now my tiles list is pointers to tiles. My edge map. So now we have to think about what this really is. So I'm going to return and I've decided that tile should be uppercase because it's more consistent with some of the other things I'm doing here. And all right, does that feel good? Not sure. Okay, so so what this is going to do is we're simply adding all of the so edge map is going to add all of the edges in a tile to a single map, which the edge gets a slice of ID. So for each tile, we're going to add its ID to the edge map. So IDs become the edge map of E. Wait, T dot edges. Oh, whoops, T. Oh, it's tile dot edges. So we want to append to that list of IDs so we fetch the list of IDs, then we say IDs so actually let's just do this append and then edge map E equals IDs. Tile.id is type int. It's no longer in type int. Now it's a type ID. And then this needs to be an ID. And I've got another error somewhere. D. Okay. So now we've got a map which contains, for all the IDs in our system, the list of tiles that have that ID. And what I'm going to do, even though it's going to print a pile of junk, I just want to see what our edge map looks like when we're done on our test data. So I see no errors. Fascinating. $23.11. So it's possible, I mean, because of symmetry, tile 2311 has edges that are symmetric, maybe? Also, so edge map is supposed to be for each edge. These edge numbers, these edge maps are supposed to be values that are less than 1024. And yet somehow I have one that is 254,976 right here on tile 2311. So that probably means that my reverse function is busted. So maybe we should figure that out before we go any further. Because I don't see any other way that I could have gotten a number that big. So let's just take and generate a unit test for this function. So reverse 10. And as I did yesterday, I'm just going to move this. It makes things a little easier to read if you do this. Get rid of the arg struct. Sometimes it's handy to have it, but in this case, my arguments, it only takes a single argument, so why bother? So test cases are so if we the value from 1 should be 512 and 512 should be 1. Let's just check those two values. Okay, it's happy about those two. So now let's try 1023, which should also be 1023. And 0 should be 0. All of those are correct. All right, so let's do so reverse seems to be fine. So did I build Did I build my edges wrong? Update edges. Oh, well, this is... I forgot the reverse part of these four. So... So let's just run this again and see what we get. Um, $23.11. E. So what I'm going to do here... Oh, this is printing edge map each time through the list, which is actually probably okay just now because I'm still trying to figure out what's happening on the first item. Tile. And I'm actually even just going to put a break here just to stop it after one iteration, just so I can figure out what's going on with that first tile. And then this string, yeah, I mean, let's just do a print. Oh, this is a useful technique here. Because I'm concatenating a string together to return a whole big string corresponding to a tile, what I'm doing is I've used a strings builder. And strings builder acts like a writer, and so you can write to it using normal techniques for writers. Since fprintf writes to a writer, you can use fprintf, you can use strings builder, you can use fprintf to write to that formatted strings, and then when you're done you return sb.string and you get the whole thing as a string. So in this case what I'm going to do is I'm going to add to the end of the string fprintln, and I'm just going to do t.edges just to see what the value in edges is. Oh, oops. SB t.edges. There we go. Just after I explained it, I get it wrong. Okay, so we're going to do that, and now we're going to run this, and it'll just give us one tile, and it'll tell us what the edges are. And so it says that the left edge... Oh, I know what's wrong. Okay, so I'm doing a vertical slice. The problem is that my vertical slice is not adjusting that slice. So it's pulling out a column of bits, but it's ORing together those bits from where they sat in the word rather than starting at the base. So let's do vert. So I'm taking the result and I'm shifting it, but I had to start by taking so vert I'm doing high bit and low bit, or a value shifted right by one. But maybe what I should do is let's do this shift inside the mask so that we have both, we know which bit we're working from so that we can shift it back. So so instead of mask, we're going to call it bit index, and we're going to say mask is bit index, is 1 shift left by bit index. And then now we can take our result and we can say the result is the result shifted left by 1, or t data I and mask. So that is the bit that we want, but that thing gets shifted right again by bit index before we mask it into the result. So now vert gets, instead of 1 shift left by I, which is going to pass it I, and here where was the other place where we used vert? Here we go. Instead of vert of high bit and low bit, all right, there, and then these two become, instead of high bit, they become high bit index and low bit index. Now, if we run this again, we should get a better answer. Oops, I shifted it right off the end. I need a -1 invert. Oops, negative shift amount. Rats. Because if bit index is 0, we're going to try to shift. Oh. Wait, that's not right. Hold on, let's see this. So I have a bit index 0, and then the mask is 1, and result is result that t data in mask. So if the mask was, bit index was 1, then the mask would be 2. Then we're shifting back with that index. Actually, yeah, I didn't need the -1 in there, but why didn't it work? Let's generate unit test for vert. Figure out what I'm doing wrong here. Oops, file has unsaved changes. Alright, so vert. Instead of doing t equals tile with all this stuff, because we don't have to, we can do t is new tile. And oh, the ID here we'll do 1, 2, 3, quote, because they don't matter. And so now our test case is going to look like our data is going to be slice of int and if we do it as our top value is 512 and everything else is a 0, no, actually let's do it as 0, 0. bit index 5. And what we want from this is 256. And what we want from all of these, because we only set one of the bits true, is for these to be 256, no matter which value we put here. And it doesn't like... Oh. Here we go. So save that, run this test, and it's correct. Arg! What have I done wrong? Alright, let's just try a couple of other values to be safe. Copy, paste, B, C, 0, 9, it's happy with all those values. So I must be doing it wrong. Why did it get 0 last time? I changed something that fixed my bug, and I don't even know what I changed, but I don't care. So now these are the values of my edges, and they all look like plausible values. And now we're going to let this run without all the prints. Definitely without the break. And we'll print the edge map at the very end. And why do I send... Oh. I don't need this. Okay. I have no errors. No obvious errors. Now let's do this. And my edge map says there are a bunch of edges that have no match because they're on the edge. There are never more than 2 matching edges. So this makes it easy. So now actually I'm going to do this same test with input data, because these guys sometimes just screw with you. And they're like, oh yeah, we didn't tell you about this. Their sample data can be misleading. And that is especially true yesterday. Okay. All of our matches are unique. I love it. So this simplifies the problem greatly. So now, as part of our edge map, what we're going to do is we have our set of IDs and we have everything in the edge map. Now we can go through for edge comma IDs. We can go through the edge map and for ID range IDs, if length of IDs is 1. We can just continue. We don't care. But here, let's do it this way, just to be safe. We're gonna do switch on length of IDs. Case 1. Continue. Case 2. Since I know it's 2 now, I can say tiles this was silly. Tiles really should have been a map as well. So our tile structure has our matches. That's what we called it. Dot matches. And matches was a map of edge to ID. So we have to figure out which edge I'm going to make an assumption, which maybe we have carefully constructed data, that no two edges on the same tile will match. Oh no, I know that's... No, I don't know that's not the case. But that the size of our edge... I'm going to return -1. No. If I didn't find a match... Yeah, I'm going to return -1. And It'll blow up at some point if it didn't find a match. So 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 find the match for that edge equals tiles equals IDs 1. Alright, and you do the same for tile 1. So basically creating pointers within each tile back to the other tile. And this becomes a 1. And this becomes a 0. So now every tile has matches doesn't like me. What have I done wrong? I think I need an extra curly brace. Yeah. Okay. Oh, I guess now we should print the matches as well in our string. So edge 0 matches tile 2971. Edge 1 matches tile 1427. 4 also matches 2971. 5 also matches 1427. So what that says is the top is symmetric for this tile, which isn't true. Because look at it. Oh. Okay, so here's the problem. I create both the primary and the flipped version of the tile. And that's true for both tiles on either side of a map. So what it's saying is that these two tiles fit either this way or this way, which is true. They do. So, but I don't want. I guess if I'm checking both the regular and the flipped versions, I don't want to compare them to the regular versions. So maybe what I can do is I can say find match. I mean, either find match or the loop down the bottom. So for I 0, I is less than length of t dot edges over 2, I all right. Let's run this again. That's not good either. If we flip the edge, okay, so my strategy of storing both flipped and unflipped edges is bad, because if I store both flipped and unflipped edges, then I can tell if two pieces fit together, but I don't know how they fit together. I don't know whether I have to flip one, because I'm always going to get two matches. So instead, we should not be storing the flipped edges. So I'm going to delete these inverse ones. The update edges thing is not going to do any more reversals. Instead, we can reverse as we're testing if we find that it fails. So if it matches, then I know that M2 must match as well. Tile M2 is this. And then if I didn't find a match, then it has to be the inverse. So I don't have to do that twice. Copy. We're just going to do rev So now see what we get. I'm guessing there's some minus ones in here now or something stupid like that. For 0. There we go. Okay, so. So those are my 4 edges. And now it's telling me the 1951 doesn't match. Okay. It's getting late and I have to do some stuff. So I'm going to end the stream. I'm sorry. Didn't get as far as I'd hoped. But hope you all have a great day. Thanks. Bye.